Again, so welcome to lecture 28. This is going to be on low frequency circuit analysis. But before starting, just some announcements. So homework number 9 is online and due this coming Friday. Lab number 5 is online. That's been online since last week. But it's going to be due on 5 p.m. on Friday, November 20th. Which is a few weeks from now. This is your first design project, so this is going to be a bit different than the other labs, and I'm going to talk a little bit more about this before starting with the actual lecture today. But just right now, let me just say that it's a design problem, and so we want you to sort of stay with it during the whole thing. It's going to involve a hand design, a SPICE design, and actually building a circuit and making sure that your circuit functions. I guess it's a significant part of your grade, this lab and the next lab, which are your project labs. And so, to make sure that you're on the ball for this, that you don't fall behind, we're going to have checkpoints. And so the week of 11/9, which is next week, we're going to ask you to have some SPICE simulated designs, or a SPICE simulated design that satisfies at least 2 of the specs in the design, and I'll show that to you in just a sec what those specs are. You have to email this to your TA before your lab section. And then the week of 11/16, and of course is 2 weeks from now, we want to see you with a functional breadboard circuit that at least amplifies an input signal. It doesn't need to satisfy all the specs yet, but at least it's functional. Basically what we want you to do is actually do something so that, when the deadline comes around, you're not in emergency mode, pulling all-nighters and that sort of thing. And so for this, you would email a photo and measured waveforms to your TA. Before getting into Lab 5, let me just say the midterm exams are nearly graded. And so maybe by tonight or something, you'll see your grade scope and you'll see the grades on the midterm exams. After that, I'll release solutions for the exam. And then Z-scores I'll have available soon after that too. So you're going to know the combined Z-scores of your homeworks, your labs, your these exams, or this exam. And so you'll know where you stand in the class pretty much by Z-score. And we'll talk again about grades and that sort of thing. I guess the lecture topics today, so I guess I'll stop there. Any questions about anything logistically in the class? Okay. So on lecture topics, we'll continue with open circuit time constant analysis, and then that was for high frequency analysis. Then we'll do short circuit time constant analysis for the low frequency part of the amplifier. And if we can get to it, we'll do introduction to inspection analysis. And if we can get to it, I'll give you some hints on lab number 5, your design project. But right now, let's look at lab number 5. So this has been online. Some of you have probably taken a look at it. But this is it right here. This is online again. And so it's going to be due Friday, November 20th. And it's basically this circuit right here. So you don't really have a choice of circuit. You're going to use this circuit. And hopefully this circuit is familiar to you by now. You've done a few homework problems on this. This is a common emitter circuit with a bipolar transistor. And you can see the what we call our stable biasing network there with the 2 resistors R1 and R2 forming a voltage divider. You have a collector resistor and emitter resistor. Then you've got these bypass capacitors, CE, CC1. We don't have a collector bypass capacitor because we're going to drive directly a load, that is your oscilloscope probe, which is a 10 mega ohm input, 15 picofarad capacitance. You'll stick a load on this of 22 picofarads here. And you see these other capacitors here. These are parasitic capacitors from your breadboard, the CPs there. Those are all about 4 picofarads there. And then you've already learned about these parasitic capacitors, C pi and C mu. We're still talking about those now, but at least you've seen a brute force design methodology to get the high frequency response. And so it's this amplifier. You'll hook this up on your board, but you need to get some very specific specifications out of this. So you really now are designing something that maybe you might design for a product, for example. These are the types of things that you would be looking for. And so you want your mid-band gain to be at least 120. And this is voltage gain, so voltage in to voltage out. You want your lower corner frequency, which we'll talk about a bit today, to be 100 hertz. You want your upper corner frequency to be 250 kilohertz. You want your rise time to be less than 4 microseconds. And you want an undistorted output voltage swing of 1.5 volts, 0 to peak. So all specifications should be met while you have this load, this 22 picofarad load. And you want to minimize all of the external bypass capacitance. So when you choose CC1 and CE, you want those to be as small as possible to make this frequency of 100 hertz. Why? Because smaller capacitors are cheaper. You need to satisfy bias stability, and so this is that same equation that you've seen in lecture. All your resistors and capacitors should be the standard 10% values. Your input resistance, RS, is 820 ohms. And again, you're using this circuit topology, and the transistor you'll use is the 2N3904 transistor, which you have in your kit. And we have the data sheet also on the website where this lab is. Okay, so this is the design spec, and throughout the next week and the week after that, we'll be talking about how to achieve these design specs. We've already kind of talked about that with the stuff that we have discussed. You already know how to get this gain. At least you know the equations necessary to get there. You already know how to get this upper frequency. At least you know the brute force equations to get there. I'll teach some better ways to do that today. And you'll soon get this lower corner frequency, which means you'll pretty much have everything that you'll need to do this lab, and to at least get a SPICE design next week on Monday and Tuesday before your lab sections. And so with this lab, it's going to be a bit different. You need to write up a report for this. And so this is something where you're writing in prose, and the report should be something that's not too long, so it should contain no more than 10 pages of text and figures. But it's going to be almost like you're writing a paper, a news article, or some journal paper or something like that. You don't need to make it 2-column format like those things. It could be single column, and in fact, that might be the best way to do it. It'd be nice to see figures embedded in a professional manner, so use Microsoft Word, use Google Docs, whatever you're comfortable using to create a nice looking report. And the format of the report should have the following things. You should have a design and strategy discussion. And this is also showing how much each of these are worth in terms of points for the total lab. You should have a hand design where you talk about exactly how you went about choosing your resistor values and choosing other values for your capacitors and around your transistor. You should have computer and SPICE simulations that confirm that at least in simulation, you can satisfy all of the specs that are right here. You should have experimental results. You're actually going to hook this up, put it on a breadboard, and test it. So you're going to measure the waveforms, measure the frequency response, measure all the different things that you need to satisfy, and show that your actual built circuit satisfies all of that. And finally, you'll have a summary in this that includes a table. And so a table of all the specs that you made and didn't make. So some of you may not make all the specs, and so the world won't end if that happens, but you'll definitely receive the highest grade if you can meet all of the specs. And so these are approximate weights here for each section, depending on how your report is written there. Just a little more detail on this. So the design strategy section, that should include a discussion of how you approach the design problems. What trade-offs in the specifications did you encounter? And so this is something where you already know the equations necessary to make many of these specs. And so you can use those equations to say, well, if I increase this, and that would have gotten smaller, and I would have not made that design spec. It's that kind of analysis, that kind of discussion that we want to see in this design strategy and discussion part there. I guess I've written some of these things here, these equations to help explain this. I should have a clear diagram showing the entire circuit topology, table summarizing your complete design. And the summary section in here I just talked about should include a table that it compares the specified parameters from hand design, SPICE, and lab measurements. You want to compare everything. Does your hand design match your SPICE, match your measurement? And hopefully it does, because one thing that this lab really teaches you is that all the things that you've learned really do work. right? All the hand analysis, all the design strategies you're learning are very much used in practical design of actual products, and you're going to be given a chance in this lab to do that. Calculations, so show all the calculations in variable form before evaluating, but just show final equations. We don't need to see you derive all your equations. We've done that in lecture already. Just show the ones that are relevant to your design that will allow you to say, these are the trade-offs in this design problem. Include plots that definitively demonstrate the results for each specification. Okay, so specifically we want to see the experimental plots and the SPICE plots where needed. In fact, if you could put the experimental and the SPICE on the same plot, that would be great for a lot of these things. All to help you sort of understand that everything you're learning, it does really work, and to understand the extent to which it doesn't really work. That when you're dealing with actual devices, just variations in betas and variations in resistor values, etc., those things can make it a little difficult to make a certain spec. And so you'll see just how far off from the SPICE simulation, for example, your experimental result can be. And all of this, you'll learn a ton just doing this lab here. This is the first design project, and so this is not meant to take too much time. Your second design project is actually going to have more transistors involved with it. Right? This is a single transistor design project. It's going to be an uphill battle to learn all of this here. It's a single transistor, but it's not going to be easy. So you have to work on it as you're doing this. You'll get help from your TAs and everything, and the lectures have taught you a lot how to do a lot of this stuff. The book will help as well, and we'll give hints along the way. But hopefully you enjoy this whole design project as you're doing it. And then get prepared for the next one, which will be harder. But by that time, if you've learned all of this, the next one actually might be easier for you, because you've gone over the hump of all the details of how to get a practical circuit work, at least on a breadboard. So with that, that is your first design project, which we're calling lab number 5. Are there any questions about this? I don't see anything on the chat, so I'll assume not for now, but please join us in office hours and everything to get as much help as you want with this lab. Make sure you learn as much as you can, because this lab will teach you tons. Okay, so back to the regular lecture parts. And so last time we did a brute force high frequency analysis. And then we started open circuit time constant analysis. So what does that mean? So last time we were analyzing this problem, which looks a lot like your lab. So we're basically analyzing your lab. We analyzed it many lectures ago, actually, for the gain across this, so Vs to V naught. So you already know those equations. We did a brute force analysis, and by brute force I mean we just plugged in the small signal circuit for the transistor here, which includes two capacitors, C pi and C mu, to model the high frequency response of this, to model the frequency shaping that a transistor actually does in a circuit. By brute force, I mean we applied KCL and KVL and just worked out all the equations. And after we did that, the answer we got was this. So if we're looking for, so let me go back one. We're looking for this frequency cutoff here, the high frequency cutoff. And so maybe I'm not drawing it so it looks like that, but this is minus 20 dB per decade coming down here. And we want that 3 dB frequency, which we're calling omega h there, at least the radiant frequency there. And so we went and used equations and Kirchhoff's current law, Kirchhoff's voltage law, circuit analysis, and we ended up with that first pole, which is equal to omega h. And so I can be a little clearer about that. Omega h is equal to that omega p1. That's the first pole that we have. In our analysis, we got two poles, actually. The first pole was a dominant pole, so it pretty much said where that transfer function would start going down with frequency. And it ended up looking something like this, where we had each of those capacitors in that circuit, C pi and C mu. Those were our small signal capacitors. And you'll recall from previous lectures that they come from junction capacitance, and they come from just some charge in the base of the transistor that's going up and down, increasing and decreasing with AC inputs. But these capacitors here seem to combine with some resistor values. So R prime was a value of resistance that we defined. R prime was basically this resistance, RS, in parallel with RBB, in parallel with R pi. So you can think of it as all the resistance in shunt with node 1. And R double prime was all the resistance in shunt with node 2. In shunt means going from that node to ground. Okay, and so that's what those resistors really are. And you can see with C mu, I also had an equation for a resistance, but this is more complicated. It includes that R prime, but and R double prime, but it also includes something that looks almost like a gain term. So it includes the gain of this thing, which is GM times R double prime, if you recall, it was the gain. And we're multiplying that by R prime, which means this is a big resistor right here. And that's going to tell us in the future C mu is going to be an important capacitor, because this is going to be a very big term that will almost dictate what omega H will be. We'll say more about that later on, but before that, recognizing that, you know, the solution here, let me go back one more here, was really just a couple of time constants that we're adding together in the denominator and then taking 1 over those there. And that gives us the frequency. So is there a better way to get these time constants? And the answer is yes. Rather than brute force circuit analysis, which takes a long time, we talked about open circuit time constant analysis. And I won't go through all the details of this, but the bottom line is that associated with each capacitor in that circuit, you can define a driving point resistance. And so that's this RJ naught. And this whole thing says what that driving point resistance is. It's effectively the resistance you get when you put a test source in place of that capacitor, and you find out using that test source what the resistance is across its terminals. It's just like finding the input and output resistance for any circuit that you've done before, except now you're doing it in places that are not necessarily at the input and output. You're doing it in some more general places within a circuit. And so this was sort of the procedure, and we went through the procedure last time. At least we started it. And so we started it, and I'll leave this up on the left side of the screen and go to the right side and get to where we ended up. So we ended up attacking that same problem again. So taking that circuit, creating the small signal circuit for that, which by now hopefully you know how to do well. I added a C sub L capacitance to this, a load capacitance to the whole thing, just to make it a little more general, and I guess a little more like your lab number 5. And then this is the first analysis that we did. And so I guess I want to put that circuit up on this side here. And so you see what we did. We took this circuit, and we're focusing now on C pi. We want to get the driving point resistance associated with C pi, because when we multiply C pi by that driving point resistance R pi naught, we get that time constant that we want. That adds to other time constants in the denominator of 1 over that summation that gives us the cutoff frequency, the high frequency cutoff. And so to get that driving point resistance, we did exactly what this thing said. We took all small capacitors, less than 1 nanofarad, and open circuited them. And so in this circuit, let me go back to this circuit here, that means C mu, that's a small capacitor, I'm open circuiting that. It's no longer there. This CL, that was also a small capacitor, 50 picofarads, is less than a nanofarad. I also open circuited that. Okay, and then you take all independent sources and eliminate them. And so here's an independent source V sub S. We're short circuiting that. And if it were a current source, we'd have to open circuit. That's what, to eliminate a current source, you open circuit. And then you short all the large coupling bypass capacitors, and that's these capacitors, CB, CC, and CE, in this circuit to create, in the end, this circuit. And so with this circuit, what we do is we replace the capacitor that we're trying to get the driving point resistance with, that was C pi, which used to be here, with a test voltage source, Vx. And we then want to determine how much Ix is, and like any resistance, we're going to take Vx divided by Ix to get that resistance. And so this is what that circuit ended up being, which really comes straight from this circuit here. I mean, this is just this circuit with C mu open circuited, CL open circuited. These two combined into R double prime. This I could have combined into an R prime, I suppose, but I didn't. But now all I want to do is get the resistance seen looking this way now. I've got ground down here, so all of this part of the circuit just doesn't matter. It's not contributing to this IX. And so I could just say right off the bat from by inspection, this IX is equal to RS in parallel with this R pi, parallel with R1, parallel with R2. And that then becomes that driving point resistance. And that's equal to R pi, which is all the resistance from this node shunted to ground. And so in the end, that's our time constant. We're just going to take that C pi and multiply it by that R prime. Okay, so we did this last time. And so now we have to continue doing this. We have to do this for each capacitor in this circuit here, because each capacitor will contribute a time constant that will contribute to the high frequency response of the amplifier. So let's now proceed to work on the time constant for C mu. So I'll do that in blue. And so here what I want to do is determine T mu naught. Tau mu naught for that time constant. And that's going to be equal to the capacitance C mu times the driving point resistance R mu naught associated with that. And the naught in this case means open circuit. That means we're doing open circuit time constant analysis. And you know why that we're calling it that, because every time I want to get the driving point resistance, I'm open circuiting all the rest of the small capacitors in the circuit. Okay, so if I go ahead and do that and I replace C mu by a test voltage source, then my circuit looks something like this. Well, first we need R mu naught, and so we're going to get it by drawing that circuit. So here's my test voltage source, Vx. That takes the place where C mu used to be on this side here. And so drawing the rest of the circuit here, I have an R pi still there. I've got VBE across that R. Well, let me combine that R pi with some of these other resistors that I see in this direction. But let me now combine it with RS so I can explicitly show that RS, the voltage source Vs from RS, I'm grounding, right? So voltage sources go to ground. And then all of this stuff here ends up being, I can call it RBB, but I'll just write it out as my R pi parallel R1 parallel R2. Okay, so I have my test voltage source. This is going to ground, and across this I have voltage VBE. And so on this side, I've got IX heading in that direction, which means my plus and minus terminals for my test voltage source are going that way. From here, I have that current source, the voltage controlled current source, that's equal to the GM of my device, a small signal parameter, times VBE. And then finally out here I have my output resistance in parallel with all those other resistances, which remember I called R double prime last time. So I'll just use that shorthand and call that R double prime there. And so what we did here was we replaced our C mu capacitance with our test source. Could be a voltage or current source. I like to stick a voltage source in there. And all the other capacitors in the circuit, the C pi and the CL, I open circuited, making this open circuit time constant analysis. And so I can analyze this circuit, but I think what I want to do is first convert this circuit into something a little simpler for me, at least to look at. And this is just showing you a trick that you can do in any circuit that you have. Anytime you have elements in series, you can juxtapose them. So this Vx is in series with the parallel combination of these two resistors here. Right? These are all going to ground there. So I can actually take Vx and stick it in the side that the resistors are at and draw my circuit like this. So there's my Vx. I'm going to take it up here. That's going to go into that parallel combination of resistors. And so that whole parallel combination of resistors, that's just R prime again. And so I'll write this out completely. So that's R pi parallel R1 parallel R2 parallel with RS. And then I have the rest of this part here, which has this GM times VBE. Well, let me put the resistance in here. Let me put R double prime there so I have more space to write this out. And this is going to be GM times VBE there. And all of these are still going to ground down here. Okay, so I've just rearranged this circuit just a bit. And so in rearranging this, note that now my VBE is going in this direction, because I moved that thing over to that side. So the way I've drawn it, the VBE now looks a little upside down. And from this, this is my IX going into there. And so from that IX, my R mu naught, of course, is going to be equal to VX over IX. Once I figure out what IX is, or Vx is, for this circuit here. Okay, so let me now do the circuit work for this. So I'm basically going to apply I can apply a KVL around this loop here. Just sort of say that this voltage equals whatever voltage is generated by the currents going through there. So let's go ahead and do KVL. Kirchhoff's voltage law. Let me stay blue here. So using Kirchhoff's voltage law, I could see that Vx is going to be equal to the current times that R prime, right, plus this R double prime times all the effective current going through the R double prime. And that's going to be equal to Ix, which is going through this, minus this GM VBE there. So I can write this as Ix minus GM times VBE. Well, I can look at this and I see, because of the way VBE is, that VBE is going to be equal to minus Ix times R prime. Just from that circuit. And so using this then, together with what I have above there, so let me join these together like this. So joining those together here, I end up with Vx is equal to Ix times R prime plus R double prime times Ix plus Ix times R prime times GM. Right? Plugging this in for VBE up here. And then finally, with this, right, I've got Vx and Ix's on both sides. On both sides. Now I stick them on the same side. I will then get R mu naught. Let me make this look a little nicer. Is going to be equal to Vx over Ix, which, doing this rearrangement, is just going to be R prime plus R double prime plus GM times R prime R double prime, which tells me then that the time constant associated with C mu, that capacitance, is just going to be equal to C mu times that resistance. So times R prime plus R double prime plus GM times R prime R double prime. And so this now is my second time constant, the one due to C mu. And if you remember what I just showed with the brute force thing, this is starting to look like that brute force equation. I'm not going to mention that just yet, but at the very end, I will compare the two of them. There is a question. Can you explain why R prime is on the right side of Vx in the circuit? Which circuit? Do you mean this circuit? So all I did was I took Vx. So if I have two things in parallel, in series. So suppose I have, let's do this in green here. Suppose I have this circuit, R1. Well, let's do it this way so that you have some source. Say I have some source, and I drive R1 and R2. Like that. R1 and R2 are in series. And anytime two elements are in series like that, I can juxtapose them. So I can turn this, whatever that source is, and make that R2 an R1, and that circuit doesn't change at all. That's pretty much what I did right here. I said, this is one of my elements, this is another of my elements, and I just juxtapose them. I move that to there and move that to there, because they're both in series to ground from that point. And so I just juxtapose those two. I had to be careful to change the polarity of the plus and minus of VBE so that it stayed the same as the polarity here, right? But that's how I was able to push R prime on this side of Vx. I didn't have to do that. I could have also analyzed it with Vx right here. It's just, for me, it's just easier to look at when I got my source on one side and I've got all the rest of the stuff on the other. Okay? So hopefully that explained it. Okay, great. All right, so we have this time constant. We have one more time constant to get. And so I think I'm going to sneak off here and come back here. We have this CL that I have to look at. So I want to determine the time constant associated with that CL. And so let me go green here. So we determine tau L naught is equal to CL times RL naught. And we get that. And so I want RL naught. So to do that, I have to do the same thing. I'm going to open circuit C mu. I'm going to open circuit C pi. I'm going to ground out Vs here. And so if I do that and I redraw this small signal circuit, I'm going to end up with the following. Rs is going to be there. I'll have R pi parallel R1, parallel R2. My VBE is going to be there. That's ground. I'm going to have my GM times VBE here. And then I'm going to have all this resistance in shunt with the output, which I called R double prime. That includes R naught and RC and RL for this circuit. And this then, because this is where CL was, is where I'm going to put my test voltage source to measure my test current going in there for this circuit. And so if I look at this circuit, this whole thing on the left side, that's all grounded. Right? So if that's all grounded, then that goes away, that goes away. And if this goes away, then I have no VBE, which means that goes away. And so in the end, the only resistance I see is just this R double prime. So I can just write right away that RLO is just equal to R double prime. Now let me be formal about that and say that's Vx over Ix is just equal to R double prime. And therefore, the tau associated with CLO, tau LO, is just equal to that capacitance times R double prime. And this is what we end up getting. Okay, and why we want open circuit analysis? Well, the open circuit analysis just comes from what we discussed last time. So you need to go to the last lecture where I talked about all of this here. So this basically says why we open circuit those capacitors as we're doing this analysis. It doesn't quite completely say that, I suppose, but it's in Cedra and Smith, and there's even more stuff in there in Gray and Meyer. But just in the end, it makes sense that you open circuit those capacitors because you're really handling one capacitor at a time. So if I'm looking at this circuit, I've got 3 capacitors in here. And so if I want to handle one capacitor, we just handled CL, and I want to get its driving point resistance, I can't have these capacitors around because they'll have another driving point resistance associated with them. So to get the driving point resistance with CL, which is all the resistance in parallel with CL, I need to eliminate these capacitors, and to eliminate capacitors, you open circuit them. Okay, I don't know if that explanation helps with that, but that's pretty much what we're doing for this here. So once we've determined all these time constants now, and so now that we've determined all the time constants, I can now write a complete equation for our high frequency cutoff frequency, which is the following. And it looks like my computer, for some reason, is having some great difficulties. It is extremely slow now. That's why I'm having trouble writing at this point. I have no idea what the reason is, but I'm going to have to write slowly here. So basically, the frequency is going to be, the cutoff frequency will be 1 over the sum of all those time constants. And so when I write that out, that's going to be 1 over a bunch of things, including C pi r prime plus C mu. This is really crippling me right now. I wonder what is causing this. Oh, it's affecting my audio too? Okay. I have no idea. Let me check and see. Okay. There's some major downloads going on right now. And I guess I'll just go slowly while these major downloads happen. That's unfortunate. Okay, but anyway, I've got C mu times, there it is up there. So R prime plus R double prime plus GM times R prime, R double prime. And then finally, I've got the amount associated with CL. That's CL times R double prime. So this ends up being my equation now for my high frequency cutoff. And really, it's a procedure. You sort of, is the audio bad while I'm writing? All right. So the audio is bad for you on Zoom, I guess, but the recording, I mean, the only saving grace, which I'm not sure is a saving grace, is that at least the recording is going to be okay. So hopefully it's not that bad here. But my computer, without a doubt, is struggling right now, and I know why. It's downloading something, and I don't. Well, it stopped now. So let's see if the speed's back. Okay, so yes, the speed's back. Finish downloading. So what I want to do is just take this. Well, we didn't have that CL in our previous analysis, so this part at least should match what we had before using brute force. And so our brute force answer, which really comes from the last lecture, right? I just threw this at you at this lecture, but you had to watch the last lecture to know where this comes from. If you look at this C pi times R prime, and this C mu times R pi plus R double prime plus GM times R prime, R double prime, these are exactly the same. Let me make sure that you can see the double prime right here. But these are exactly the same now. And so that should give you confidence that the analysis I just did, which seemed to take a while, but once you get used to it, it can go very fast. But the analysis I just did is very much correct. Okay? And so there you have it. I've done it two ways. Brute force to get the high frequency response, and then this open circuit time constant analysis, which I highly recommend you use to get the high frequency response. Okay? You will be doing it time and time again. If what I showed you looked confusing and you have to go through it again, then go through it again when you watch the video or just looking at the notes that I post. But you'll be doing this again and again, and practice makes perfect. If you practice more of this, and hopefully for your Lab 5 design, your design will be horrible. Your first design is going to be horrible. And if the first design is horrible, that's the best thing that can happen to you. Because what it's going to force you to do is iterate to get to the final design. And as you iterate to get to a final design, that's going to force you to use this equation again and again and again and again. And if you do that, you'll get really good at this, which means when you finally have to take a final exam or something, or when you get to your next lab, lab number 6, which includes more transistors, you're going to have a much easier time with it. So for this kind of stuff, practice definitely makes perfect, right? believe me, if you want to get good at this, you're going to want us to throw tons of homework at you, which we won't do because we need to respect your time. But in terms of learning, that's the best way to do it. If you have time to do more problems than what we assign you in homework, do them, because you'll get better and better at this. And at a certain point, it's going to become fun to you. I know it doesn't seem that that's true right now, but previous generations of this class, this is going to get really fun. And this is where people really enjoy circuit design, because they can apply these techniques and just design circuits out of nowhere, analyze circuits out of nowhere, and look like they're extremely smart people, which they are, but they can make themselves really look smart by taking a big circuit and saying, oh, that's what it does, in just a minute. All right, so let's go take a look at the other side of this problem. So there's one more aspect of this problem that we need to finish, and then that's going to give you all the things you need to do for your design. So back to this right here. We have the mid-band gain. We have the high-frequency response. Now we want this. I want to know where this cuts off here, and that's low-frequency response. And so that's something that I'm not going to do a brute force derivation for. I'm just going to head right into the technique for doing that. And the technique for doing that is short circuit time constant analysis. So for high frequency, we have open circuit time constant analysis. In this case, we have what's called short circuit time constant analysis. And it's obvious why we're going to do that. We're going to do that because we're going to short the capacitors. But the capacitors we're going to care about now are these big capacitors, CB, C sub C, CE. This is what causes this roll-off to low frequencies. And so if I go on this side here, I'm looking for omega L. I'm looking for that cutoff where the frequency is going up, but then it stops going up and it flattens there. That happens because of a pole. Right? A zero causes this to go up. Then I hit a pole, and then it stops it from going up 20 dB per decade. It makes it flat. And so in general, for the low-frequency response, the transfer function is going to look like this. It looks very similar to the high-frequency response, except now, instead of having more poles and zeros, now you have the same number of zeros, both n sub L in this case, as poles. When you have that situation, you're going to get something like a high-pass filter. And if we have a dominant pole, which means that one of the poles is much larger than the rest of them in this system, then we can use a similar analysis to what we did to do open circuit time constant analysis. And so if you didn't watch that lecture, you need to watch that lecture. Otherwise, you're not going to understand what I mean by dominant pole. But in this case, a dominant pole is the highest frequency pole out of all the other poles there in this case. And so that dominant pole is going to be a frequency here. And so in this equation, this E sub 1 is going to be omega P1 plus omega P2 plus so on and so forth, omega Pn sub L. I add all of these together to make E1, and this E1 effectively is going to be the location of that pole, which is omega L. And so the transfer function for this F sub L, as we know, must look like this, S over S plus omega L. So if we take all this complexity, which includes all sorts of other poles, but we want to condense it down to one pole that dominates over the rest, that it condenses down to S over S plus omega L. If looking at this right here, we can see that that omega L is just going to be that E1 right here. And E1 is just the sum of a number of frequencies that in the end come from all the capacitors. And so this omega L is equal to E1 is the sum of a bunch of these frequencies, which in the end are the sum of 1 over time constants. And so we're going to do the same game. We're going to find capacitors, we're going to determine time constants for them, but now we're actually going to calculate their frequencies, and we're going to add together all the frequencies, where 1 over the time constant, of course, is frequency. Okay? And so this is the equation that we're going to use here. And so, whoops, I can do the same type of definition here. Specification. The CJs in this case are no longer the small capacitors, but they're the large capacitors. Large capacitors, at least for us, being greater than 10 nanofarads. The driving point resistances we want to get are the driving point resistances across CJ. They're we're going to get them exactly the same way we got the driving point resistance for the open circuit time constant analysis. Except that in this case, all the large capacitors, we're going to short circuit them now. Because for large capacitors at low frequency, short circuiting them makes it look like they're not there anymore when we're doing the analysis. So if I'm analyzing CB, I short circuit CC and CE to get rid of them in the circuit. And then we replace the capacitor that we're interested in, which we don't short circuit, but we just replace it now with a test voltage source, the same way we did for open circuit time constant analysis. And just like open circuit time constant analysis, all independent sources we eliminate. So if we have any voltage sources, we short them. If we have any current sources, we open them. And for any of the high frequency capacitors like C pi and C mu, we're not going to deal with them. And so getting rid of them, in this case, since they're small capacitors, is the same as opening all of them. Okay, that eliminates them at this frequency. So at this very low frequency, these capacitors look like open circuits, is really what we're doing here. Okay, and like I did for open circuit time constant analysis in the last lecture, there could be a case where you don't have a dominant pole, and in that case, if you really want to fudge it, and this is not entirely accurate, let me say, but you can use this equation where that low frequency pole is going to be equal to omega p1 plus omega p2 squared, so on and so forth, minus 2 times omega z1 squared, that is the location of a 0, minus 2 times omega z2 squared, etc., for as many zeros as there are in this. And so I will say you will never use this equation. I'm just telling you this equation in case you get to a point, well, you never use this equation in this class, but in case you get to a point where you do not have a dominant pole in this case, then you can use an equation like this. If you want an approximate answer, it'll be very approximate. It will not be that great of a value either, but at least it's something. Okay, so with that, explaining sort of what this procedure is in words, which is never the best way to explain it. Probably the best way to explain it is to actually do it. And so let's now do it to that problem we were looking at before. So here's that problem again, exactly the same as this, except now I want that low frequency response. I want this response right here. And so let's hop to it. Let's go ahead and do this here. And let me start with C sub B. Let's start with this capacitor here. And I'm getting low frequency response again. So I'm already red there, which I want. So A. Let's get C sub B. So to get C sub B, I'm going to short circuit the other capacitors. So I will short circuit C sub E and C sub C, and then determine the driving point resistance for the C sub B, which I'll call R sub BS, where the S stands for short circuit. Okay, and so same procedure. I'm going to replace CB by a test voltage source. And so just looking up here, there's my test voltage source, plus minus there. On this side, I'm going to have a resistor, and I'm going to ground out my source like I said we would. This is now going to go into that parallel combination of R's, which are, I guess I called that RB before. So I'll call it RB here. I guess I could have just written out R1, R2. And then the rest of the transistor equivalent circuit. So I'm going to have an R pi here. I'll have my VBE right here. So hopefully you're getting used to drawing this small signal circuit by now. I guess later on I'll ask you not to draw it, but at least at some point you should know this circuit fairly well. So you have GM-VBE there, and then out here I still have that total resistance out here going to ground. So all of this goes to ground because I've shorted CE. This is going to be R double prime. And remember that R double prime was equal to R naught in parallel with RC in parallel with RL, which to me is really RC parallel with RL. And so this then becomes the circuit that I want to use to determine the driving point resistance for C sub B. And so if I look at this, the way I should look at this is just a voltage between two resistors here. I effectively have Let me get to where I am. So I effectively have this circuit here. I've got my Vx. If I call this, say, R11, and that R22, right? Same thing, I can juxtapose these two here, put Vx on that side, and then I'm going to see R11 here, and R22 there. These are ground. And so if I look in this direction from that test source, and I can go ahead and try to measure that test current there, but really no need there, because I could see right there that total resistance seen in that direction is just R11 plus R22. So just right off the bat, by inspection here, if I see a voltage source like I have on the left between two resistors that are each going to ground, I can just add those two resistors together to get that driving point resistance. So in this case, RBS is going to be Vx over Ix, which is going to be Rs plus all the resistance I see looking down here, which is going to be R pi in parallel with that RB. And so in the end, my first time constant I can write as CB times all this resistance, Rs plus R pi in parallel with RB. That's my time constant, but what I'm going to be adding in the end is going to be a frequency. So let's go ahead and turn this into a frequency right now. Call that omega Bs. That's going to be 1 over this tau Bs, which is going to be 1 over C pi, CB, times this resistance, Rs plus R pi in parallel with RB. So that ends up being that frequency that I'm going to add to the frequencies contributed by the rest of these capacitors here. So let's go ahead and do the next capacitor. Let's do let's do C sub C since it's the easier capacitor right now. That's a capacitor just right at the output here. And so it's going to look like a similar sort of thing. I'll draw the whole circuit out though first, just to be very complete. So this is B. I'm looking at capacitor C sub C. I'm going to short circuit the other capacitors. So I'll short circuit CB and CE. So that's my short circuit time constant analysis. Then with that, I want to determine the driving point resistance associated with capacitors C sub C, and I have to zero out my source, which is V sub S. Okay, so if I do that, looking at the circuit up here, and plugging in my small signal circuit, zeroing out V sub S right there, I have Rs coming in there. I have that string of bias resistors right here, RB. I again have R pi with voltage VBE across it. I again have this GM times VBE, part of my small signal circuit. I have this resistor here, which is now R0 in parallel with RC. And then I have my test voltage source, V sub X, which I am replacing C sub C with. And then finally I have my load resistor out here, where my test current is heading in that direction there. Okay, but I have the same thing again. I have a voltage source here between two resistors. All this is going to ground, by the way. If that's going to ground, then I have no voltage across any of these resistors back here. So as far as I'm concerned, these resistors aren't here. The VBE goes to 0, so that also is nothing. And so all I really have in this circuit are just these two resistors here. And I've got that voltage between those two resistors. That's exactly the same situation up here. And so I can just write the driving point resistance, RCS, as just being equal. So that's equal to my Vx over Ix. But that just is going to be equal to the series combination of RL, sorry, not RS, but RL, plus my R0 in parallel with RC. And so, since R0 is so big, to me this is really just RL plus RC. I wouldn't even bother calculating R0. And so I did that again because R0 is much greater than RC, I assume, which is generally a safe assumption. And so in the end, I can write that that time constant, tau CS, is equal to C sub C times RL plus RC. It's one of the equations I care about. And that then leads to an omega CS equation, which is 1 over tau CS. That's equal to 1 over that thing, C sub C times RL plus RC. And that's my second frequency that I'm going to add to the first one in order to get my low frequency response, the cutoff, my low frequency cutoff. And I think with that, I've got one more to go, but the one more to go is going to take more time. Maybe I'll set it up though. Let me just set it up for the last one. And maybe you could try this on your own before the lecture. I will do it. But let me just set this up for you. Let me use that color there. And so the last one that I have, let me put the circuit back in here, is this C sub E. And like I said, this is going to be a bit more difficult. So let me, oh no, let's use green here. Let's get the frequency associated with C sub E, and like we did before, you take the other capacitors not involved, CB and C sub C, and you short them. And you also zero out your source V sub S, and then in the end, we want to determine the resistance RES. Okay, and I'm just going to set up the circuit for you here. And so this circuit, this C sub B is going to be shorted, so I'm going to see RB going down here and RS going there, and I'm going to short out my VS, which is that right there. I just shorted it out. So I have RS here. I have RB there. I have my R pi. And my VBE across that R pi. I have the rest of my small signal circuit. Of course, I've open circuited my small capacitors, so you don't see C mu there, for example. So I have GM VBE. Over here I've got a resistance R0. And then back here, finally, I have a resistor RC parallel with RL. But here's where the difficulty comes. Now I want to replace C sub E with a voltage source. And so here's the Vx that I'm going to replace it with. I'm going to measure the current Ix going in. And I also have at this point a resistor hanging off of this RE. That's still there now because it's no longer shorted by the CE that used to be there. Should the polarity of Vx be flipped? Are you talking about this circuit right here, Naomi? Is this the one you mean? Oh, the last circuit. It actually doesn't matter. It only depends on which direction I took Ix for. So in this case, I'm taking Ix to go that way. But it doesn't matter if Vx is flipped or not. Basically, anytime I see a voltage, whoops, that's not the circuit, but anyway, that's the way Ix should have been. Okay, this circuit is what you want. No, yeah, see, for here it doesn't matter which way Vx is going, right? It's consistent with the Ix, right? I want the Ix coming out of the plus in that case. Okay, there you go. All right, so with this, let me stop. So what I'm going to do next is I'm going to analyze this. But this is more difficult to analyze than all these things that I've been doing so far, except for the resistance with C mu, have basically been inspection, right? I basically looked at them. I could have looked at them and just said, this is what it is. And that's what a lot of your problems will be. And so hopefully with that, you're starting to see how we can get to the point where we can look at a big circuit and know what it's doing within a minute. Because it really comes down to inspection and just seeing things, identifying things, knowing those things, and then being able to write down almost immediately what the frequency response is, what the gain is, etc. But we'll get there. But you get more and more of these examples, and we'll continue with this in the next lecture. So again, probably by this evening, you're going to have your grades out with your exam, and then we'll release solutions to that, and then we'll talk about your z-scores probably in the next lecture. Okay? But everyone, have a nice day. Go ahead and vote. Please vote, whatever you do. If you haven't voted already, please vote. And enjoy your voting day tomorrow, and I'll see you on Wednesday.